You're so behind. Oh my god. This is like 3 on the base. Look at me. Oh, it's
Any questions on the at-home critical lecture? All right, so today we're talking about energetics and biochemical reactions and how we can use that to think about right now to sort of think about what does the delta G value mean, but in the long run, we're really going to be examining delta G values of different reactions. So understanding what that means here and how to calculate that is important. The free energy is a measure of useful energy that's capable of doing work, potentially, if it is harnessed in a certain way. You can also release energy of heat, but in the cell, especially if reactions that are proceeding through metabolism release energy, usually we want to capture those in cell so that we can then use that energy to do work. So when describing reactions, we use a term called delta G, which is the difference in the free energy of, in this case, the products, if we're going in the forward direction, the products minus the free energy of what the reactants were. And that will give us a delta G, a change in G in terms of the forward direction. And so if we have a delta G in the forward direction that is negative, less than 0, we can say that that reaction in the forward direction is exergonic. It releases energy. And that term sometimes is called spontaneous. I don't love that term because it implies that the reaction just happens because the delta G is negative. And that is not the case. Just because a delta G is negative does not mean that reaction happened out of control. Okay. In the long run, we'll talk about activation energies and how enzymes help facilitate reaction. So I'll usually say favorable. Favorable meaning a delta G is negative. If a delta G is 0, that means the reaction is at equilibrium. We would have an equal tendency to form products as reactants. It might be going back and forth, but it's happening at the same rate. So there's no net formation of products or reactants at that state. Delta G is 0. And if a delta G is positive in the forward direction, that reaction does not take place spontaneously. It's not favorable, and it's called endergonic. In order to proceed, it would require an input of energy. And fine, we have ways that the cell has ways of getting reactions that are endergonic to happen. We'll talk about how that works. Okay, questions on those concepts? All right, so this table sort of just summarizes that if a delta G is negative, there's potentially free energy produced in that reaction that is available to you. Now, importantly, a delta G value, the quantity or the value of it doesn't indicate how fast a reaction is happening. So you can have something that's very negative. It doesn't mean the reaction is fast. That is usually controlled by the enzyme. So how fast is the enzyme catalyzing that reaction? That really controls the rate. Okay. So you can have a delta G that is quite small in the forward direction, but the enzyme's really fast, so it happens very fast. Okay. Now, sort of exploring the idea of delta G, what is the Gibbs free energy equation that you learned at home? The basic Gibbs free. Delta G is equal to yes. delta G is equal to delta H minus temperature times delta S. Okay, so all those two things, the enthalpy and the entropy, are going to contribute to the delta G of the reaction. And we'll look here at ways in which each part of those equations, or the values of those parts of the equation, contribute to a delta G here. So we'll look at 3 examples. Each of these cases, the delta G for this reactions going forward is negative. So are those reactions favorable?
Yes.
Yes, they release energy, they're exergonic, potentially energy capable of doing work. But whether or not both the delta H and the delta S contribute to that favorability can be different. Okay. So let's look at fermenting glucose to ethanol. This is the reaction. The delta H here, the enthalpy, it decreases, so that part of the equation contributes to a negative delta G. And then this part of the equation, we take into account temperature, and then we take into account entropy. Does entropy increase or decrease in this reaction going forward? Entropy increases. Yeah, it actually increases. Entropy increases. And because we're multiplying that by a negative temperature, the value is a negative. So entropy is increasing. The delta S part of this is increasing. So the random nature of the products here are more than the reactants. And that makes sense. You often see that when you're going from a solid to gas. You're usually increasing entropy relative to the reactants. Okay, so just keep in mind there that the entropy is actually increasing, and therefore the total value here is negative because we're multiplying it by a negative. So in this particular case, both the entropy change and the enthalpy change are both contributing to a negative delta G. Okay, fine. Now, this equation here, or this reaction, combustion of ethanol. Delta G, is this favorable? Yeah, releases a ton of energy there. Mostly due to our delta H, very negative. Does the entropy increase or decrease? Now, the entropy actually decreases a little bit, meaning the delta S is a negative value. And when you multiply it by another negative, it becomes positive. So the entropy decreases a little bit, but because the enthalpy increases so much, the delta G is still negative. So this is just showing you the point that you could have one part of the equation not contributing to a favorability, and the other part does, and the delta G is still negative. All right, in this last case, the delta G is negative 30 here, decomposition of nitrogen pentoxide. In this case, the delta H is positive. So the enthalpy is increasing in value. What is the entropy doing there? Is it increasing or decreasing? The entropy is increasing. Yeah, so delta S is positive, but the negative delta T makes this very negative. So the entropy is actually increasing a lot, enough to overcome the positive delta H and still make this a spontaneous exergonic reaction. Okay. All right, so you can also envision that the change in entropy is going to have more or less of an effect on the delta G depending on temperature too, right? If you have a high temperature, the entropy change is going to have more of an effect on the delta G. Okay. Most of the time in biological systems, our temperature isn't varying widely because we're talking about living systems. Their temperature probably isn't changing too much, especially humans, but keep that in mind, the temperature would have an effect. Questions on any of those examples or comments? These are not numbers you need to memorize. It's, understanding what's happening here. Okay, so theoretically, all reactions could go forward or in reverse. All right, they are theoretically reversible. So you will see they're written like this: a forward or reverse rate. But whether or not we actually see this happening, especially in a cell, is going to depend essentially on how great a delta G value is. So if a reaction is very negative in the forward direction, like this, getting this to go in reverse is going to be really difficult. We would have to have a huge input of energy to make this go back, right? And so in our pathways, our biochemical systems, what ends up happening is that the truly reversible reactions are going to be pretty close to zero. They're going to have very little either negative or positive delta G in the forward or reverse reaction. And therefore, you can force them backwards or forwards by changing concentration of products or reactants. And we'll talk about how that actually works. Okay? And just keep in mind, when delta G is zero, the reaction's at equilibrium. So the forward and the reverse are still happening, but just at the same rate. So there's no net production of one of these. Okay, so if we have a generic reaction like this, and we add A and B, and we let the reaction happen, at a certain point, the reaction will come to equilibrium. If there's no enzyme there, it might be really slow, it might be years. But if there's an enzyme there, the reaction will come to equilibrium fairly quickly. And then you will be left with a certain amount of concentrations of the products and a certain amount of concentration of the reactants. And that's called the equilibrium constant. Whatever that ends up being, that will be the equilibrium constant for that reaction. Are these all going to be equal? Not necessarily, right? Probably not. That will depend on we'll get to the delta G naught prime in a minute. But okay, let's say we let this come to equilibrium. There's a sort of net formation of products and reactants at that point. Delta G is zero. What would happen, what do you think happens if we add a little bit more of A and B? Will it stay at equilibrium? Yeah.
It's going to shift more towards the products to like maintain equilibrium because you're adding more, so once like balance out.
Yeah, so it's sort of intuitively we know that like it's probably going to go in the forward direction again. So all of a sudden, when you change, you add more A and B, we're probably going to force it in the forward direction again. Right? We're not at equilibrium anymore. And so now the forward direction is favored. That means we made the delta G forward a negative value. Right? We're now favoring the forward direction because we added A and B. So what that's telling you is that you can change the delta G, right? By changing concentration. Okay? We just changed it so that it was favorable in the forward direction. Okay, so that's important to keep in mind. Delta G can be changed depending on the concentration of products and reactants that you have. Okay, so lots of information here. All right, so how can we think about this, and how can you relate chemical reactions to each other? So people understand that delta G can change the favorability of a reaction, but if you want to do some comparisons between reactions and think about favorability of certain reactions overall, you want something that is definable. And so delta G's can be defined as standard conditions. And then that gives you a number that it does not change and allows you to compare different reactions. So a delta G is defined under standard conditions, and we call that delta G naught prime. So for biochemical reactions, standard conditions are at the state you're starting, the reactants and products are all at 1 molar. The temperature is 298 Kelvin, And the pH is 7, which means that hydrogen ion concentration is 10 to the minus 7 mole. That's pH 7. So if you have all reactions given at this standard state, then you can calculate a delta G, and that's a defined number. That won't change. Okay, and so that you can look those up for any particular reaction in a table. You can say, okay, I'm looking at this reaction. This is the delta G naught prime for that. And now you can sort of compare reactions and favor. Okay, that's fine. We have those values, but we know then in most situations, we don't have 1 mole of reactants and products, especially in a cell. 1 molar is a lot. So most of the time, we do not have 1 molar. So how do we relate those two? We say we know the situation at standard state. We know that's not the case. We know our concentrations. What is the true delta G in this particular condition? And that's where we get this equation here. And this is something you should be able to work with. And we'll go over some examples. All right, so this relates delta G, which we know can change, just said it can change, to a delta G naught prime for a reaction. And it allows you to vary the concentrations of products and reactants that are present currently. And so that changes the delta G naught prime value depending on current concentration. R is a gas constant that will not change, and temperature can potentially change. So you can plug in whatever temperature you're at. Okay. If we are at just standard conditions, room temperature, it would still be 298. If you're at body temperature, it becomes 310 because that's 37. And then you take the natural log and you can plug in current concentrations, which are whatever your concentrations of products are over your concentration of each reactant. Sometimes you'll see this represented as just Q. Sometimes you'll see it written like this in a simpler way, but this is actually telling you what you have to plug in to find out what Q is. Okay, questions about that calculation? We will do that. Okay, so if we are looking at delta G naught prime and also thinking about, we said that at equilibrium, what is delta G? Is 0, okay? So in this particular circumstance, if we said, and this kind of relates Q to equilibrium constant, let's say at equilibrium, we know that delta G is 0. So if we said that at this reaction was at equilibrium, we plug this in for delta G would be 0. And then we move this part of the equation to the other side, so it's now negative. We know when an equation is at equilibrium, we define that this ratio was actually the equilibrium constant, right? So instead of being variable at delta G, the ratio of products to reactions could be defined as the constant. So remove delta G from this equation. And so you can actually relate these two. The delta G naught prime, which we know is a certain value and doesn't change, is also directly related to the equilibrium constant. So those two are relatable to each other. So if you know one, you can figure out the other, and so on. So this is a particular circumstance where we're at equilibrium, and these ratios, instead of being Q and they're variable, they're actually equal to the equilibrium. Okay, so we can see in tables like this, if we know a delta G naught prime, we also know what the equilibrium constant is, which is the concentration of products and reactants at equilibrium. So if we kind of just look at one of these numbers, a delta G naught prime, this is a positive value. So does that mean a forward direction is favorable or unfavorable? Unfavorable. And so what this is saying, if we have an equation that has a positive delta G, if it's at equilibrium, there's gonna be almost no product, right? The equilibrium constant is 10 to the minus 5. So it's highly, highly favored in the reverse direction. So that shows how delta G naught prime relates to what a ratio would be in equilibrium. Okay, questions on that? We'll do the calculation so you can see how we calculate. Okay, let's first, we're looking at kind of this equilibrium constant related to delta G here and how we can use one to figure out the other. So this is an example of a reaction from glycolysis. This reaction actually is reversible in the cell, going back and forth between glucose 6-phosphate to fructose 6-phosphate. The delta G naught prime here is very close to 0. It's 1.7 kilojoules per mole at standard state. So if we started off with 1 molar of each of these standard state conditions, which direction is favored for that reaction? Yeah, the reverse reaction. It is positive in the forward direction. Therefore, if we start off in standard state, 1 molar of each, it's actually favored to change the fructose 6-phosphate into glucose 6-phosphate. And that would happen until delta G becomes 0. Okay. So if we know this delta G naught prime, we can actually figure out at equilibrium how much of each we would have. Because we can plug that in to this equation. So the equilibrium constant is equal to E to the negative delta G naught prime, which is this number. I have changed it from kilojoules into joules because our gas constant is in joules. And then temperature, we're just saying is 290. Okay, so we're just plugging these numbers in and we get an equilibrium constant of 0.5. That tells us at equilibrium, we will have about half as much fructose 6-phosphate as glucose. And we're just gleaning that based on this delta G naught.
A question on the last slide.
Yeah.
So if you're saying that the K prime equilibrium is 10 to the negative fifth, isn't that indicating that concentration of A and B is super high compared to concentration C and D?
Yes.
So then wouldn't it want to go towards the forward direction to like if the concentration of the reactants are super high to reach equilibrium?
So that's what it will be at equilibrium.
Okay.
But remember, standard state conditions is starting off at 1 molar of each. So if you start off with 1 molar, it's driven by this number, that delta G, to go in reverse. And then if you let it get to equilibrium, you're left with almost no C and D.
Okay, so that's
Yeah.
the result.
That's the result.
Okay.
Yeah, exactly. Yeah, good question. Yeah. Okay, so that's how those two are related. How you can figure out an equilibrium concentration, or sorry, a ratio relative to delta G naught prime. Now let's plug in, and I know this is very busy. Let's plug in and figure out a true delta G. We're calculating a delta G for a particular reaction, given a set of concentrations that are given. So this is the equation we're using. This is this equation. But we're doing it for a particular reaction. And the reaction we're looking at is the hydrolysis of ATP by water. And we're just removing one of the phosphates on ATP. So this is a very common reaction in cellular conditions when we're using ATP for energy. We'll get into that. Okay, so the delta G naught prime for this reaction, we know is a defined value. That doesn't change, and so you can look that up. So delta G naught prime for hydrolysis at pH 7.4, this will come into play because that is not standard state, is negative 32.2. So that is the number we'll plug in to our delta G naught prime value. And then we will just need to plug in the various current concentrations of the products and the reactants. When you see a water in an equation like this, we can ignore that because any one reaction is not going to wildly change the concentration of water in a cell. So we don't have to deal with that as a value. We just call that 1 and cancel that out. Standard state conditions were such that pH is 7, and this reaction is happening at 7.4. So because we have a proton concentration, proton as one of the products, we need to deal with that. So most of our standard state conditions are 1 molar, but pH being 7, standard state for that is 10 to the minus 7 molar. That's what the concentration of protons are at pH 7. We have to put that in the equation. These are the other concentrations of products and reactants, and we'll plug those in. Notice they're in millimolar, so we're changing those to molar because standard state is in. Okay, so we're plugging everything in here. Delta G we're trying to find. This is delta G naught prime. We plug that in. This is the gas constant. This is our temperature. Natural log. Now, these are the concentrations of the products. So one of their products is ADP. It's 0.1 millimolar. So that's 0.0001 molar. We're dividing this by the standard state value. For one thing, you always want to compare current to standard state, but we also need to get rid of the units. Otherwise, we're left with a strange number of moles in this part of the equation. So we're getting rid of units here by dividing by standard state conditions. Because it's 1, there's really no effect other than getting rid of the moles. Okay, so that's ADP. Then the phosphate concentration is 35 millimolar. So that's 0.035 molar divided by 1. And the protons, we said that pH is at 7.4. So that's equivalent of 10 to the minus 7.4 molar divided by standard state proton concentration, which is 10 to the minus 7 moles pH. So, okay, those are all our products. Units will cancel out nicely. And this is our reactant. We said we can ignore 1. So the only reactant is ATP concentration, which is 5 millimolar, 0.005. Okay, lots of numbers. Any questions on why we put any of those in? Okay, plug that all into a calculator. And what we get, you can have to believe me here, is this part of the equation altogether ends up being negative 17.1 kilojoules per mole. So we add that to what the standard state delta G naught prime was, and delta G is negative 52.5 kilojoules per mole. So at these concentrations, this reaction going forward is more favorable than it was at standard state condition. Why is that? That's probably because we have less product than reactant. Probably more reactant going to being driven to make product. Okay, questions on doing those types of calculations? All right, it'll probably take you a minute to go over this, these types of calculations, but These are sort of plug-in type calculations, even though it looks very busy. Okay, so what's interesting about delta G's like this for different reactions is if you couple reactions, if you can get them to occur together, maybe in a sequence or in the same active site of an enzyme, they can be additive. So the reaction going from A to B plus C, that's unfavorable. That's endergonic. It would require energy. But if we are able to then couple the production of B to making D, that's quite favorable. And so if you can couple those two together, you can add them. And the entire net reaction is favorable. So we will often see things like this reaction, ATP, which is favorable for most of the time, being used as a coupling reaction to get unfavorable reactions to proceed in the cell. So this is an example. This is our ATP, has these 3 phosphate groups on them. If you remove one, it is favorable, like we talked about. You can even remove 2 of the phosphate, and it's even more favorable. So if a reaction requires more energy, you can remove both phosphates, the cell. And there's quite a few reasons why this is favorable. Removing one of these phosphates removes all of these negative charges that are right next to each other that tend to be repelling each other. So if you remove a phosphate that is released, a released phosphate can adopt different resonance structures. So it has a more of a random conformation that it's locked into. So the entropy of that drives this favorability. And the released phosphate is better at interacting with water. So there's a lot of energetic reasons why removing the phosphates are favorable. This is looking at, this chart looks at a lot of different molecules that have phosphate contained on them and the favorability of removing those phosphates. Here's our ATP, somewhere in the middle. You can see other molecules here, if you remove their phosphates, release even more energy. And we'll see some of these in some of the pathways we talk about. But as an example, we'll look at this creatine phosphate. Anyone heard of that? Some people take that as a supplement. That is, you can see that removing the phosphate from creatine phosphate releases more energy than does removing one phosphate from ATP. So what's interesting about this and what happens in the cell is that removing this phosphate from creatine releases energy, and that is used to reattach the phosphate to ADP and remake ATP, because that's positive value there. That requires a lot of energy. So in the cell, most stores of ATP get used up quite quickly if you're exercising. The cell doesn't store a ton of ATP. So when I say used up, I mean the phosphate gets removed and provides energy for a reaction. Well, if you want to remake that ATP, you have to reattach the phosphate and recycle it, right? So the recycling of that requires energy. So we can couple those two reactions in the cell. ATP gets used, meaning the phosphate gets removed to fuel a reaction, but we want to reattach that phosphate and recycle it. So then the cell also has some storage of creatine phosphate, the phosphocreatine. Removing that phosphate releases more energy, and we can use that energy to reattach the phosphate to ADP and remake ATP. So those two reactions can be coupled. And the net reaction essentially uses phosphocreatine to remake ATP, and it is still exergonic coupling. So those are things that happen in the first moments of like heavy exercise, and then the body goes into regular metabolism, where you're remaking ATP by glycolysis and all of the other pathways. So these are happening in the first few moments. Questions on that? A little tidbit you can bring up at the gym. Yeah.
So even though it's getting closer to zero, is it like technically favorable?
Yeah, so this negative is still very favorable, especially when you think about like the ratio here. So even though it seems low, you're still highly favoring that forward direction. So like if it was a -12, it was about that. It's still about 10 to the 2. It's still favoring products at 100 to 1 ratio.
Okay.
Yeah. So it seems like a small value, but it is quite favorable. I wish I could get rid of this. But yeah, okay. Want to leave you guys enough time to work on the problem set, so we'll go ahead and open.